in contrast to the last one, where we found we had the population standard deviation, so we were able to do the z-test. So this one's a one sample t-test. So we got to assume here that the population value isn't known. All right, so it is known that the population of incarcerated 15-year-olds, the average score on a standardized measure of hyperactivity is 25, sort of out of a total of 50. More high scores reflect more hyperactivity. To explore the effects of a new drug, researchers administered a drug to a sample of 40 juvenile delinquents. The obtained sample mean was 23, and the unbiased sample standard deviation was 5. It is hoped that the new drug reduces hyperactivity. Test the hypothesis using an alpha 0.01 and show all 7 steps. So first thing, you may be wondering, why is 40 sort of highlighted or bolded and underlined? Because in the practice problems, this exact same setup is there. It's just, it refers to 400 juvenile delinquents. And I was just trying to, when I was redoing this, I'm like, let's make this a little bit more realistic so it's not a massive sample, and just use 40 and see what happens. See if that makes a difference in terms of testing a hypothesis. Right, so this is different than that one. So we're getting different answers. That's why this is only 40 instead of 400. So again, let's walk through what we know. All right, let's try to figure out what's given to us and what we actually can use for our study. So, all right, incarcerated. So oftentimes with word problems, some of the hardest things to figure out is what things are relevant and what things aren't. So you see the number 15 here, 15-year-olds, and sometimes you might be tempted to assume that the 15 is something relevant. All we've done here is sort of identify the population. So our population is incarcerated 15-year-olds. So this 15, the number is not important at all, except for defining who our population is. So don't be lured to thinking that 15 is somehow important. The average score on a standardized measure of hyperactivity is 25. So that's in the population, right? The measure of hyperactivity, the average is 25. So we're given that the population mean equals 25. That's something that we're actually provided with. But it doesn't say anything about the population standard deviation, so that's not there. So to explore the effects of a new drug, researchers administered the drug to a sample of 40 juveniles. All right, so let's talk about that's population. This is what we know. What do we know about our sample? All right, our sample has an n equal to 40. The obtained sample mean was 23. So our mean sub x equals 23. With the standard deviation, S equals 5. All right, so that's what we know about our sample. The only thing we know about our population is that it has a mean of 25. That, by the way, is the clue. So you may be thinking, well, all right, if sigma is there versus not there, right, that's sort of signaling to you about whether you're doing a z versus t. The fact that you're given the population mean at all is what's signaling to you that you're doing sort of a one sample test, because you have to have something like a population mean to compare your sample to. If you don't have that, it's so you have nothing to compare your sample to, right? So you have to have some kind of population value to compare it to. So this sort of indicates that because we have the population mean, at least, we are going to be doing a one sample test, but we don't have the population standard deviation. Sigma is missing. So we're going to do this as a t-test instead of as a z-test, right? So t is what we're going for. What other things are important? Well, again, make sure, this is one of those cases where assuming 0.05 is not okay, because it does say use an alpha of 0.01. So we're given a different than sort of normal alpha level. All right, so we're giving a 0.01 alpha level instead of a 0.05. So let's talk about we'll figure out how that affects the test in just a second. But let's start to do this. So we know the sample stuff, we know the population, we know we need to sort of switch up our alpha. So let's go through and figure out what this looks like. So what other words should I look for in here? So it says, it is hoped that the new drug here's another big word, that it reduces. So reduces indicates direction. Had this said something like, the reason it is hoped that the new drug changes hyperactivity or has an impact on hyperactivity or something like that. Those kinds of words may lead you to think about a two-tailed test. The fact that it just has reduces, right? The attained sample mean, blah, blah. So it is hoped that the new drug reduces hyperactivity. So we're testing to see if giving participants this particular drug lowers their hyperactivity. So that is indicating a direction, like directly to our alternative hypothesis. So let's figure that out. Let me kneel down here a second, start kicking things around. So we now have to do the seven steps. The first step is let's state our null, first two null and alternative. So step 1, step 2. I need the null and alternative hypotheses. Okay, so we know that there's a population value of 25. And again, that statement of whether or not the drug reduces the hyperactivity tells me a direction. And that's really giving me what should be in my alternative hypothesis. So that means that I think that the mu, it's always stated in terms of mu, even though we're really thinking that our sample is lower, we're going to state it in terms of mu. I think mu is less than 25, because 25 is our sort of target population value we're comparing it to, and I think that it's going to be less than that. If that's true, and that would mean a reduction, right? That if since higher numbers mean more hyperactivity, getting a lower number on this hyperactivity scale would mean lowering hyperactivity. So that's what reduces is talking about. I think it's going to be lower than 25, which means my null is going to be the reverse. All right, so that means I'm doing this, and it's going to include the equal sign. Because if it ends up equaling 25, well, that's not very impressive either. So they all got a drug and they stayed the same. Right? So the only way that this is going to work is if they get a drug, they take this drug and their hyperactivity is reduced, something less than 25. So if they're either equal to 25 or more than 25, that's not evidence to support the drug, right? It's not reducing anything. Step 3, we said that the alpha is equal to 0.01. That's stated in the problem. Right, so it's no longer, we can't just assume this 0.05 like we normally would. It's stated that it's we can't assume it's 0.05 like we normally would. It's stated that it's 0.01, so we need to use that. Step 4, what kind of test is this? Well, again, because it's stated right at the very top, but things to look for, you're given the population mean, but not the population standard deviation. So this is going to be a one sample t-test instead. Right. Step 5, we need to find my critical value and state my decision rule. So now we're looking for a t critical instead of a z critical. So I need a t critical with how many degrees of freedom? Well, I have 40 juveniles, so that means my degrees of freedom is going to be 40 minus 1 equals 39 degrees of freedom. And I need to find that at alpha equals 0.01, and it needs to be one-tailed. All those things are important into figuring out exactly what our t-critical is going to be. So we need to go to a t-table, find 39 degrees of freedom, if it's there. And we need to find a value for alpha equals 0.01, and it needs to be one-tailed. All those things need to apply. So let's go to our t-table and see if we can't find a value for that. I'm going to scroll down a little bit until we come to the t-table, which is here. So the t-distribution. So again, we want one-tailed, so we're sticking with everything up here, and I need the one-tailed test that's at 0.01. So at 0.01, I'm going to scroll down till I find 39 degrees of freedom. Now, I did this sort of on purpose because if you notice, there's 38 and there's 40. You have a choice. You can either try to figure out what the number might be. You can add these two together, divide by 2. You might get a midpoint somewhere in there. So the value I want somewhere between 39 and 40, because the table doesn't include 39. So now I have a choice, right? What do I do? The easiest thing to do is, of the two, 38 and 40, the critical value for 38 is bigger than the critical value for 40, right? Because smaller degrees of freedom means larger critical value. So you could, one thing I suggest is just to pick the critical value with the closest degree of freedom that doesn't go over. So 38 is less than 39, and find that one and use that one instead. Again, you could try to find exactly what the number might be, but it's not quite going to be right anyway. So let's just stick with that. So I know 2.4386. 2.4386 is going to be too big. It's going to be a little bit too large because it's for 38 instead of 39. But if my t observed is bigger than that number, then I can be satisfied that it's going to be bigger than it would be at 39. The problem is if it's close, I may have to come back and revisit this. But as long as my t observed is bigger than this, then it's also going to be bigger than a number for 39. And I can feel pretty satisfied that that's the case. Okay, so we're going to use a slightly bigger number. So this is t critical for 38 is 2.4286. 2.4286. So this is 2.4286, and I can even indicate that this is going to be sort of roughly equal to this because 39 isn't there, right? There is no 39 in the t table, so I'm just getting, you know, the value that's closest to it. Basically 2.43, something like that, is a number we're going to use, and we'll see how it goes. If my t observed is too close, I may have to sort of rethink that. But so my decision rule is, again, this is a one-tailed test. So if my t observed, TO, is greater than 2.4286, I'm going to reject the no. Okay. So I can go to step 6. Actually, I'll do step 6 here. Step 6 is going to be to find t observed. So t observed equals my sample mean minus the population over S sub m. Okay. So this is going to be 23. Actually, I realize there's an issue over here. 23 minus 25 over 5 is my standard deviation, and I have 40. So n equals 40 here. So that's going to be my standard error for the mean. So what I mean by, as soon as I put down that my sample is 23 minus 25, the population, I realize something's wrong here. So one of the things you want to make sure of is that whenever you're doing this, that the direction of this should be the same as the direction of your alternative hypothesis. And I violated my own sort of rule, right? Because I don't want to know, where am I looking? When I have my t distribution, because it's one-tailed, I want to know if it's lower than. I'm saying I want the mean is less than 25. So this is 25. I want it to go that way, right? So in reality, what I'm looking for is a value. If my sample and population are the same, I expect this to be 0. But because I'm expecting my sample to be lower than my population, that's going to be a negative number. 23 minus 25. I'm expecting a negative number. So I need to know if it's more negative, right? This is a negative direction. So this critical value really is, it's not 2.4286, it's negative 2.4286. Right? It's a negative number. All right, so I gotta fix this. This is not whether this is greater than it should match. It should match the alternative here. So this should be less than, and because of that, this isn't 2.4286. My t observed should be less than a negative 2.4286. So if my t observed is less than a negative 2.486, it's more negative, less than, I'm going to reject a null. Now it makes more sense why I should be getting a negative number here. Because if I'm subtracting my sample minus my population and getting a negative number, something was goofy because I was hypothesizing a positive number here because I forgot to match this to that. Okay, so 5, go back to my, remember that this is s over the square root of n. That's how we get our standard error of the mean. So that's why it's 5 over the square root of 40. So what's the square root of 40? 40, I should clear that up. 40 square root is 6.325. So this is going to equal, this is going to be negative 2 over 5 divided by, this is 6.325. 6.325 is my, when you take the square root of 40, 6.325, make sure I did that right, 40 square root 6.325. So if I take my negative 2, well, first let's take 5 divided by 6.325. 6.325 equals 0.791. So this is going to be negative 2 divided by 0.791. So 2 divided by 0.791 equals 2.528. So that's going to be a negative 2.528. Okay? Negative 2.528 is our t observed. That's my step 6. Right? Step 6, subtracted my two means, found my standard error of the mean to be 0.791. That's the 5 divided by 6.325. Took my negative 2 divided by 0.791, so it's my difference over my standard error. I got a negative 2.528. All right. So I can go back here, step 7, and say, since negative 2.528, right, is greater than, not greater, see, I'm just so used to doing it that way, is less than my negative 2.4286, I'm going to reject the null. Now, let's think about that for a second. So again, a second ago we said there was a problem because we didn't have 39. 39 didn't exist on our table, so we used 38. And 38 gave us a slightly larger than we should have critical value. This one's a little bit too big. But we said, all right, well, if our t observed is larger than this value, it's larger than it would be for degrees of freedom at 38, which means it's also larger than it would be at 39, because at 39 is going to be a little bit smaller. So we can feel safe that because we rejected it at 38 degrees of freedom, we would also reject it at 39. Or 40 or 41 or any other larger degrees of freedom. So that's sort of the logic behind it. We don't have to actually do any interpolation between the values. Just find the larger of them. If it works for the larger one, it'll work for that one as well. So since our t observed is more negative, right? Our value is farther negative, farther out there than our critical value, we're going to reject a null. So remember the null said, I'm expecting a value that's either going to be equal to 25 or greater than 25. That would mean I would have gotten either 0 or a positive number. I didn't get those. I got a number that's far enough out in the tail for me to believe it's not there by chance. Therefore, I can reject the null hypothesis because of that. All right. So our negative 2.528 value here, that change in 2 units, is enough for us to believe that the drugs are significantly reducing the hyperactivity in those 40 juvenile delinquents relative to the population.